Welcome, everyone. My name is Jeff Bryan of the Volpe Center, part of the U.S. Department of Transportation. I'm your host on this webinar, the second in a series of webinars today. We're going to be covering track configuration. And again, I'd like to introduce Richard Cogswell, engineer with FRA. Dick will be our main presenter.
Greetings, folks.
I'd also like to introduce Jared Fitzikowski of the Volpe Center, who will co-present with us.
Hello.
So, Dick, you'll present today and other webinars on what you've called Railroad 101. Could you elaborate on what we'll cover and why we're doing it?
Essentially, to be able to plan railroad changes or new infrastructure, people need to understand some basics regarding these topics: train types and performance, track configuration, basic operations, signal systems, and train operations. So for all who are working on rail projects, we want to impart some of these fundamentals. Also, when intercity passenger rail service and infrastructure projects are done with federal dollars, FRA wants to ensure the changes are freight and commuter neutral and add capacity to the railroad.
Okay, well, let's get started. Thanks. And with this session, let's go over what you're going to cover specifically.
Okay, the purpose of this webinar is to address the areas where grantees have problems, to answer the common questions. Where, how, and why do I modify the track? Do I need a passing track here or there, or a number 32 turnout somewhere? Is a double track main line warranted? For track configuration, the question is frequently, how do I add capacity to the corridor?
So in track configuration, which we're covering today, we're going to review definitions of track elements and then talk about the characteristics of single, double, triple, quadruple track railroads and how to add capacity. In the next webinar, we're going to take that information and the train types and combine it to talk about basic operations, where we're going to review the goals for operations, discuss capacity, and how to affect it. So let's get started with some of the track element definitions. Jared, could you go over these?
Sure. Some of the definitions we'll cover are the railroad track as a composite, the track elements, which include track types, spurs and sidings, and connections, and the class of track relative to allowed speeds.
All right. So just to, before we start, just want to clarify what might be a point of confusion, the difference between class of railroads versus classes of tracks. And so, Jared, could you go over what the classes of railroads are for us?
Sure. The three classes of railroads are described in statute and in the Code of Federal Regulations 49 CFR 1201 based on annual operating revenue. Class 1 is $250 million or more. These are the giant freight railroads that own the majority of tracks in North America. Class 2 are those that are less than $250 million but are more than $20 million, the regional railroads. And Class 3 is $20 million or less. Those are the short line railroads.
Okay. All right, let's talk about the railroad infrastructure itself. So, Dick, start us off.
Yes, the railroad is a relatively delicate, precisely balanced system to distribute loads. First, you got the steel rails, spikes, steel tie plates, cross ties, ballast, subgrade, and of course this all sits on the railroad right-of-way.
Ballast, it seems underappreciated?
Yes, you're correct. People may not understand all the functions it performs. It supports the tracks and distributes the load of the track and train to the subgrade. It restrains the track, providing drainage for the track.
All right, so next we'll go over some track types. There are three track types: tangent or straight track, curved, which is any track that is not 100% straight or tangent, and spiral, which is a curve whose degree of curve varies. Dick, can you explain these track types further?
Try to. For each type of track, this drawing shows the train's center of gravity. The spiral is the transition from straight to curve with super elevation.
Could you define super elevation for everyone?
Super elevation is changing the cross level of the track to allow balanced higher speed through the curve. The change in the cross level keeps the center of gravity down through the middle of the track. so lateral and horizontal forces are minimized.
So on this next slide, we see spurs and ladder track, often in industrial areas.
Yes, typically these are unsignaled spurs with hand-thrown turnouts. A spur is a piece of track connected to another track at only one end. A ladder track connects two or more of these spurs.
And here we see an unsignaled siding.
Yes, unsignaled sidings are relatively common in single-track territory. They are built, like any siding, to add capacity to the rail line and flexibility of operations. The signals are not included to save money. The downside is this: without signals, the train must travel at restricted speed on and through the siding. Per 49 CFR Part 236.812, restricted speed is a speed that will permit stopping within 1/2 the range of vision, but not exceeding 20 miles an hour.
So because of this speed restriction, can it take a long time for a train to exit the main line?
Absolutely. Unsignaled sidings can gobble up capacity on the main line, especially if the railroad is curved and the train engineer can't see very far.
So unsignaled sidings can really reduce railroad capacity.
Absolutely.
So how would you compare unsignaled sidings to signalized passing tracks?
Signaled passing tracks, without a doubt, add to the capacity of the main line. A fully signaled track is an auxiliary to the main line. It facilitates meets and passes because the signals will allow movement in and out of the passing track at the speeds associated with the turnout sizes, not restricted speed.
So signaled passing tracks are capacity builders.
Yes, sir.
All right, so let's talk about the next element in the track configuration. That's the blocks. And what are those?
Well, blocks are track segments between interlockings.
Okay, and how does a planner or designer determine the limits of a block?
The block is based on the length required to break a worst-case braking train to a stop, typically 2 miles long. The block will typically allow any train to stop within it.
Okay, so we talked about signals at sidings. What about the signals at the blocks?
Blocks have what are called automatic block signals, ABS, that are governed by logic connected through the electrical track circuits which detect the presence of trains or obstructions. The automatic block signals indicate whether the track ahead is occupied and typically only allow one train per block.
Okay, so the blocks are between interlocking. So can we talk more about what is an interlocking?
An interlocking is a standalone dispatcher-controlled element. Interlockings on the BNSF, for example, are dispatcher-controlled from the center in Fort Worth, Texas. An interlocking can be a single turnout or a more complex arrangement. Distance between interlockings can be as low as 1,000 feet in urban areas or up to 30 miles in rural areas. At interlockings, the track, switches, and signals work in unison. They are electrically interlocked for safety.
Okay, so in this slide, using the illustration that we have a westbound train, how would you explain how they work in unison?
Well, the dispatcher first sets the route. This means that he electronically throws the switch, then he electronically requests that the signal be cleared for a route. The interlocking signal indicates what is detected through the track circuits. If something is detected, for example, a train, or if there is an ice mass or rock in the switch points, the interlocking signal won't clear. If it is cleared, the train can operate in accordance with the signal, and the train proceeds. Note that if the train was going to make a diverging move, the switch would have to be thrown by the dispatcher prior to the signal being cleared.
Okay, so let's take a moment to consider what we've covered so far, to consider how the railroad is a totally controlled environment.
Yes, consider these. Access to the railroad is restricted. It is a sealed system. Moving through an interlocking requires the dispatcher to authorize it. The automatic block signals allow only one train in a block.
So how does this control manifest itself in dark territory?
Okay, in dark territory, there are no track circuits, no signals, but the totally controlled railroad environment still exists. Train movements are directly controlled by dispatchers, communicating via radio to the trains involved.
All right, well, that's helpful, Dick. So before we go on to the characteristics of single, double track, etc., let's touch on in this slide the classes of track as opposed to the classes of railroad and the allowed speeds for each class.
Okay, briefly, you can see the class up here starts with accepted track, no passenger trains allowed, 10 miles an hour for freight, and it slowly works up to class 5, and if you really want to go off the deep end here, class 9 is 200 miles an hour with no freight. So these are in the federal regulations. This is something people don't fully realize. You see the maximum speed permitted by the different classes. Now, I would say that most mainline track today is class 4. For class 5 or greater than 80 miles an hour, positive train is required per 49 CFR section 236. Class 7 and 8 track now exists only on the northeast corridor.
All right, and there's a few more definitions that are important to capture here before we go on to the single and double track. Jared, would you go through these for us?
Sure. A turnout enables trains to be guided from one track to another. It is curved track, mechanically controlled by a switch. Turnouts occur at all spurs, sidings, and junctions. The point of switch is where the switch causes the rail to shift to allow the train wheels to divert to another track. The point of frog is the intersection of two rails.
Okay, that's helpful. So, Dick, are the words switch and turnout used interchangeably?
Pretty much, yes. It's the whole arrangement of the rails and mechanisms associated with either merging or diverging tracks.
So moving on to frog, the frog provides support for the wheels and a way through for the wheel flanges.
So, Dick, are frogs considered special track?
Yes, they are custom built, cast of manganese steel, a very strong, high quality steel, and literally in the case of a frog at a diamond crossing like shown above, they are calculated not only in degrees but minutes and actually seconds of an arc.
Right.
And moving on to crossover. Crossover connects two tracks.
Yes, crossovers are used to connect double track mains or a main line and long passing tracks. Later we will go over typical distances between crossovers in double track mains.
Okay, now that we have the basic definitions down, let's start to talk about the different kinds of track. And Dick, give us an overview of what we're going to hear about.
Well, what we're going to talk about is the breakpoints in traffic type and density. For example, when you need to start thinking in terms of a double track main line, how to add capacity through track modifications.
Okay, so we're going to start with single track. And my understanding is that in the U.S., of the 100,000 route miles of Class 1 railroads, 80 to 90% are single track, and that all regionals and short lines are single track.
That is pretty much correct. There's only about 15% or around 15,000 route miles in the U.S. that have 2 or more tracks. An important capacity rule of thumb: a single track can manage 15 to 25 trains per day with fairly good comfortable. Note that for a person standing beside the track will probably appear unoccupied most of the time.
Okay, so for that single track, how can we add capacity?
Well, first off, if it does not have it, you install appropriately spaced signals in between passing tracks. This will allow trains to operate in either direction under full signal indication. Then install additional signalized passing tracks with dispatcher-controlled switches to allow trains to meet and overtake in a timely manner.
Dick, how often are signalized dispatcher-controlled switched passing tracks recommended?
FRA recommends 10 to 15 miles in rural areas, perhaps more frequently in urban areas, especially if commuter trains are on the line.
And how long should the passing tracks be?
Well, since a typical freight train is in the 6,000 to 8,000 foot range these days, 2 miles is sort of a good rule of thumb for a passing track. It can accommodate most braking distances. Even better is a passing track 4 miles long with a universal crossover in the middle to allow trains from both directions to meet, as well as simultaneously allowing an overtake from either direction on the main line. Signals and dispatcher control switches are necessary for the trains to exit the main line quickly.
So the length of the passing track and its signaling are important for speed. What about the size of the turnout?
Okay, the size of the turnout is necessary for trains to exit the main line at the best speed. And the table will give you a description of what the turnout sizes are, everything from number 10s to number 65s, and what the typical speeds are. The higher number turnouts facilitate train slowdown without coming to a full stop. Note that the faster speed turnouts do require longer lengths. I would also add that perhaps a century ago, the largest size turnout in use was a number 10. So all of these higher number turnouts have been invented, developed, and put in service since, say, 1900.
So moving on, another way to add capacity for a single track railroad is at junctions. A junction is a place at which two or more rail lines converge or diverge.
Yeah, 2 ways to add capacity to a junction are these. Locate a passing track immediately off the main line at the junction. So if there is an inbound and an outbound train, you have a place to park the outbound train while waiting for a potentially late inbound train to arrive, or vice versa. At high density junctions, typically with double track, installing parallel routes so inbound and outbound trains can meet at the junction without stopping helps a lot.
Okay, so for those folks doing planning, installing passing sidings is expensive, right?
Yes, you are effectively building a 2-track railroad here and there. You must consider the location and topography. In mountains and in cities, it is difficult simply because of the space required to build it. Curves, should be noted, constrain capacity. Why are curves installed? For such reasons as avoiding grade changes and difficult topography, and reducing the amount of real estate required.
Okay, well, that's real helpful. So let's go on to the next category, the double track world. And we already noted that only 15 to 20% of all Class 1 railroad route segments have double tracking. Dick, when is double tracking really used?
Well, typically a double track main line starts to be really warranted when you're running more than, say, 25 trains per day. A double track railroad exponentially increases the capacity of the line. Many double track routes handle 70 to 80 trains per day. The photo happens to show Route 128 station outside of Boston, Massachusetts. It's a 2-track railroad with platforms on both sides.
Okay, so just like we talked about with the single track, what are some ways to improve capacity that will permit more traffic and reduce delays?
Well, first off, if you don't have it, you need to install bidirectional signals. This is the first thing to be done so that you can run either direction on either track. Insert universal crossovers between the mains at a uniform spacing. Install more signal passing tracks to give additional windows. These are not typically needed as frequently as in single track, but they are still needed. You can see we have noted them at 30 to 40 miles apart, whereas in the single track world we would suggest 10 to 15 miles apart. When you get to 80 trains a day and you have these densities around the country, crossing over from one track to the other can get very difficult.
Okay, so anything else we can do to improve capacity?
Yeah, typically a fourth thing that can be done, sometimes relatively easily, is to join adjacent passing tracks to provide what is basically a very long passing track and these are very useful in providing non-stop overtakes or meets. On the upper diagram, the westbound train on the passing track stops and waits for the train on the main line to pass. On the lower diagram, both westbound trains can continue at their own speeds.
And anything else for the double track?
Well, a fifth action that can be done, and this is frequently overlooked by many of the passenger advocates, is to add station platforms to both tracks, not just for passenger convenience, but to make good use of the railroad's existing capacity. With one platform, trains on the outside track must cross over to reach that platform. Crossing over takes time and space on the railroad, and on a heavily traveled route, crossing over can delay many trains in both directions. An example is shown in the photo. This is the Buffalo Depew station with a single platform. This station is on the Empire Corridor, whose traffic includes roughly 80 freight trains per day and 8 passenger trains per day. For passenger trains to cross over to reach the single platform, Amtrak currently factors in almost an hour's worth of pad to cover the 300 miles from Buffalo to Albany.
Or having a double platform is a real good investment.
Installing a second platform with a stair and elevator is a lot less expensive than building a third track. It's a relatively cheap capacity improver. If you have only one passenger per day, like Elko, Nevada, for example, it can be too costly to do this. But for routes like the Empire Corridor, it makes sense. On the topic of stations, remember that ideally the track at the station is level and straight. This is not always possible, but we need to try to do it.
And it's a good reminder. Okay, so let's move on to the triple track railroads. And what kind of traffic conditions require triple track main?
Well, a triple track main is typically used for areas with commuter service. An example is Chicago to Aurora, as shown in the photo. On this route, per day, there are roughly 100 commuter trains, 65 freight trains, and 8 Amtrak trains. 2 tracks are typically used for inbound moves in the morning and 2 for outbound moves in the afternoon. The center track changes direction. Amtrak train and Metra commuter zone expresses, which skip the stations near Chicago, will use the center track.
And what can you do to boost capacity on the triple tracks?
Well, for both triple and quadruple track railroads, locate universal interlockings, crossovers, about every 5 to 6 miles. This is twice as many as we indicated for double track mains. The primary reason for the 5 to 6 mile spacing is the significantly greater train density that is running on these triple or quadruple track main lines. Also, if something goes wrong on the railroad, the trains can't afford to run 10 to 12 miles to go around the problem, especially if they got a bunch of commuter stations in between.
And the tighter spacing of universal crossovers better accommodates track maintenance too.
Absolutely. It also better accommodates access to the commuter stations along the line also.
And this photo shows BWI station with 3 tracks. Does the whole Northeast Corridor have a triple track main, Dick?
No. Between Baltimore and Washington Union Station, the main varied between 2 and 4 tracks. But there are 4 tracks from New Haven to Wilmington, Delaware, as shown in the next slide. Except for 15 miles north of New York City and roughly 7 miles south of New York City, there are 4 tracks on the Northeast Corridor from New Haven to Wilmington.
And as we know, the Northeast Corridor from Boston to Washington sees about 2,000 trains per day, including the Acela, Amtrak regionals, the commuter trains, and about 65 freights. And there's 450 trains per day on 2 tracks, 1 per tunnel, right under the Hudson River. So with the quad track, how does that operate, Dick?
Well, typically with a 4-track railroad, the middle tracks are for high-speed trains or zone expresses. The outside tracks are commuter rail and freight. Commuter zone express trains may run on the middle tracks at 90 to 100 or more miles per hour until it can come to an interlocking before the station where they need to make their first stop. Then they cross over to the outside track, where the average speed drops to 30 miles an hour as they make numerous station stops. The moral of the story, if you're fighting track conditions and slowdowns and infrastructure elements that constrain capacity, it makes no sense to be totally obsessed with maximum authorized speeds.
I get it. So it's having realistic expectations, making the changes that one can make, and making the most out of the latent capacity that already exists.
Absolutely. You have to understand your constraints on speeds are due to numbers of tracks, size of turnout, spacing of sidings or crossovers, junctions, absence of signals on double track main line on passing tracks, spacing of the crossovers, number of platforms at stations, etc.
Okay. Well, thanks. So now we're going to just end with the requirements for planning and design. And why do the requirements relate to, or how do the requirements relate to track configuration and basic operations?
Well, railroad projects involve many parties. Our FRA grantees, probably a host railroad or two or three, probably Amtrak, commuter rail or other rail operators, possibly a bridge commission that handles movable bridges, the affected owner of land, real estate, right-of-way, and others. For each railroad project, the planned track, signal, station, and operational changes need to be understood and agreed to by all parties in writing. All parties need to agree on what the job is and regarding construction, especially if the work is interfacing with an operating railroad. The upfront agreement by all parties must describe how the job will be staged for construction.
So essentially, you need to get everybody around the table, try to get benefit for all, develop an agreement, and finally sign off from each party.
That's right. For each phase, certain information must be agreed and documented. The monitoring procedures describe this fully. See the procedures 32A and 39 in particular from the FRA website address shown. I will briefly cover it. At the end of preliminary engineering, you need to have track configuration and basic operations figured out so that it works for all users of the railroad. And it needs to be documented in scale plans showing track, signals, stations, right-of-way, real estate, various site conditions, etc. Also in the document are sequencing plans and a construction schedule that integrates the track and signal modifications into the operating railroad. All of these documents include the construction staging needed to include in the upfront agreement, the sign-off package with all the parties. The sign-off indicates understanding that if a party subsequently decides they absolutely have to have a change, fine, they will pay the full cost of that change. Only after all this is done do you embark on final design. When the project is intended to go to a design-build contract instead of a design-bid-build contract, there is even greater need to freeze all of these things up front. Changes after a design-build contract is signed, well, it gets ugly.
Yeah, I bet. Well, thank you, Dick. That's it for the second webinar. Thanks to Dick Cogswell and to Jared and all of you.